A single lightning strike releases billions of joules of energy in a fraction of a second, carving a path of plasma through the atmosphere. These extreme displays of power, along with the crackle of a synthetic sweater in dry weather, are the macroscopic results of the interaction between positive and negative charges. This connection was first documented in ancient Greece, where Thales of Miletus observed that amber, when rubbed with wool, could attract light objects like straw or hair. The word electricity is derived from the Greek elektron, meaning amber. In our daily lives, matter usually appears electrically inert. This is because the trillions of protons and electrons within an object are typically balanced, resulting in a net charge of zero. This leads to a specific mechanical question. If an object is electrically neutral, does it stop exerting force on its surroundings entirely? Absolute neutrality is often an illusion of scale. When we look closer, we find that opposing charges are rarely in the exact same location, and that small spatial separation prevents the forces from ever truly canceling out. The simplest model for this interaction is the electric dipole. It consists of a pair of equal and opposite point charges, plus q and minus q, separated by a fixed distance, 2a. Mathematically, the net charge of this system is exactly zero. We describe the strength and orientation of this system using a vector called the dipole moment, p. By convention, this vector points from the negative charge toward the positive charge. Because these two charges are physically separated by the distance 2a, their individual electric fields originate from different points in space. As we move around the system, we find that the fields from the positive and negative charges overlap. But because of that physical gap, they can never perfectly erase each other in 3 dimensions. This failure to cancel creates a net electric field. Its direction and strength are not uniform. They depend entirely on where the observer is standing. The electric dipole demonstrates that a system's net charge does not dictate its influence. Geometry does. First, consider the dipole axis, the straight line passing through both charges. We'll place a test point P at a distance r from the center, positioning it closer to the positive charge. The nearby positive charge exerts a strong repulsive field at this point, pushing directly away from the dipole. The negative charge also exerts a field, but because it is further away, its attractive pole is significantly weaker. Using the principle of superposition, we subtract the weaker attractive field from the stronger repulsive field. The result is a net vector pushing outward. This net field vector points in the exact same direction as the dipole moment vector, p. When the distance r is much larger than the separation gap, the math simplifies. The field strength on axis is proportional to the dipole moment divided by r cubed. On axis, proximity is the deciding factor. Because the observer is always closer to one charge than the other, the field is forced into a parallel alignment with the dipole moment. Now, move the observer to the equatorial plane, the line that bisects the dipole center at a right angle. At this location, the distance to both charges is exactly the same, meaning the magnitudes of the two fields are identical. The positive charge pushes away at an upward angle, while the negative charge pulls in at a downward angle. To find the net result, we deconstruct these angled vectors into their vertical and horizontal components. Because of the perfect symmetry, the upward and downward vertical components cancel each other out to zero. The horizontal components, however, add together. They create a net electric field that points in the exact opposite direction of the dipole moment. This results in the equatorial equation, where the field is again proportional to 1 over r cubed, but with exactly half the magnitude of the axial field at the same distance. On the equator, symmetry neutralizes the perpendicular forces, leaving a resultant field that runs strictly anti-parallel to the dipole moment. To understand the significance, compare this to a single point charge. An isolated charge follows the inverse square law, its field strength decaying as 1 over r squared. With a dipole, at a very large distance, the gap between the two charges shrinks toward zero. From this perspective, the opposing fields from the positive and negative charges aggressively overlap, nearly annihilating each other. This near cancellation causes the dipole field to drop off much faster than a single charge. It follows a 1 over r cubed decay. That 1 over r cubed signature is the mathematical evidence of a system where internal forces are actively fighting each other rather than projecting force cooperatively. These derivations are not just theoretical models, they govern the behavior of the matter that makes up our world. While some molecules like carbon dioxide have perfectly centered charges, polar molecules, such as water, have a permanent offset between their positive and negative centers. When we look at these molecules from a distance, their electrical influence no longer depends on the individual charges or the exact atomic spacing separately. Instead, the field is dictated entirely by the product of those values, the dipole moment. This rapid field decay and the specific geometric alignments we've discussed are what allow complex materials to react to external electric fields. Ultimately, an electric dipole proves that even a neutral system can shape the space around it, provided its opposing forces are separated by distance. That tiny gap dictates a strict geometric alignment and a rapid fade into the void.